Hello all, welcome to Chemistry EduHub channel. Today we are going to discuss the acidic nature of phenols, which is the most important concept. So let us see what are phenols first. Phenol is nothing but the phenyl ring or the benzene ring. When we replace one of the hydrogens with OH, we are going to get the structure of phenol. Simply, this is considered to be an aromatic alcohol. Benzene ring with OH group is an aromatic alcohol, which is generally called phenol. Now, the acidic nature of phenol, if we are going to discuss, we need to look at the stability of its phenoxide ion. Stability of the phenoxide ion. Now, what is phenoxide ion? Whenever from the phenol, if we remove the proton means hydrogen without any electrons, just the H plus if we remove, the bonded pair will shift on to the oxygen, and that will result in the formation of phenoxide ion. This is the structure of phenoxide ion. So based on the stability of this ion, we decide the acidic nature of phenols. Suppose if there is an electron withdrawing group. Electron withdrawing group is something which will pull the electrons from O minus. That will stabilize the phenoxide ion by reducing the negative charge on the phenoxide ion, and the stability increases. Now that will result in the more acidic nature of phenoxide ion and the phenol. So acidic nature also increases. Similarly, if there is an electron releasing group, suppose if there is an electron releasing group, already there is negative charge on the phenoxide ion. Here, if the electron releasing group is still adding electrons onto the phenoxide, so ultimately the stability is going to decrease. When it is less stable, the acidic nature also will decrease. These are the two main factors that will explain the stability of phenoxide ion and also the acidic nature. Now let us see the acidic nature of phenols with few examples. Consider few examples like simple phenol, then we have phenol with NO2 in the para position, and we have phenol with methyl in the para position. Now this is simple phenol with no other groups. This is para nitrophenol. Para is nothing but the 1,4 position. If this is your first carbon, 1, 2, 3, 4. So 1,4 position is considered to be para. Para nitro, this is para cresol. Okay, so since there is hydrogen in the para position, we consider the minus I effect or minus plus I effect of hydrogen, which is least. But if you consider NO2, NO2 is a strong electron withdrawing group, whereas methyl is an electron releasing group. So the stability will follow the order like 2. Second is more stable compared to, otherwise I'll give the directly positions. So this is first most stable, this is second most stable, and this is the third most stable, because electron withdrawing group is going to increase the stability, hydrogen is neutral, and electron releasing group will destabilize the phenol. So this way we observe the electron withdrawing group increasing the acidic nature of phenol and electron releasing group decreasing the acidic nature of phenols. Let us see the acidic nature of phenols with same electron withdrawing group. We have phenol, we have orthonitrophenol, that is at 1,2 position. Then we have metanitrophenol. Then we have paranitrophenol. So since in the first molecule there is no electron withdrawing group, this will be least acidic. Now NO2 being the minus R group, its effect is greater at ortho and para positions. So accordingly the second and fourth molecule should have equal acidic nature, but orthonitrophenol is less acidic compared to para-nitrophenol. Orthonitrophenol is less acidic compared to that of the para-nitrophenol. This is because para effect is greater, and also in the case of orthonitro there is intramolecular hydrogen bonding between the nitrogen of nitro and the hydrogen of OH. Accordingly, there is intramolecular hydrogen bonding and the tendency to lose proton is decreased because of this extra stability gained by intramolecular hydrogen bonding and this chelation or the ring formation. Due to the ring formation, the tendency to lose proton is decreasing. Accordingly, the acidic nature decreases. So, phenol less than metaphenol, metanitro, electron withdrawing behavior at meta position is least. So, first least acidic is phenol, second least is metanitrophenol, third least is orthonitrophenol, and the top position is given to para-nitrophenol, or else I'll give the positions this way. So the order of acidic nature is para-nitrophenol takes the first position, then comes the orthonitrophenol, then comes the metanitrophenol, in the least position there is phenol. So this way, though the same electron withdrawing group is present at ortho and para, because of the intramolecular hydrogen bonding, the tendency to lose the proton is decreasing, and accordingly the acidic nature is decreasing. Let us see one electron releasing group example also. So there is phenol, there's orthocresol, this is ortho, then there is metacresol, this is meta, and there is paracresol. Now CH3 is an electron releasing group at all the positions. Now I'll give numbering like this: 1, 2, 3, 4. So either the plus R or minus R effect, or plus I or minus I effect, it is greater at ortho and para positions and least at meta position. So accordingly, now the electron releasing group is destabilizing the phenoxide ion, so such effect is less at meta position, and obviously when there is no group the effect is even more better. So 1 is more acidic compared to 3 because at meta position the electron releasing effect is less. Then comes the para position, then comes the ortho position. So this is the order of acidic nature given in the case of phenol with an electron releasing group. Now let us see the acidic nature of acids or carboxylic acids. Carboxylic acids are those with RCOOH functional group. R is an alkyl group, COOH is the main functional group of acids. So acids are generally acidic, this is very common. This acidic nature of acids, not all acids are of equal acidic strength. Their strength also will differ according to the stability of the carboxylate ion. Just like we have seen in the case of phenol, here also based on the stability of carboxylate ion. What is carboxylate ion? It is RCOO minus. This is nothing but the carboxylate ion. So based on its stability, the acidic nature will vary. Most of the carboxylic acids and sulfonic acids are more acidic compared to that of the carbonic acid, that is H2CO3. Accordingly, whenever these carboxylic acids and sulfonic acids are added to mild base, that is baking soda, we observe the immediate reaction, and that can be seen in the form of white effervescence formed in the solution. So most of the carboxylic acids and sulfonic acids are more acidic. Now, what will increase the acidic nature of these acids? The electron withdrawing group. Whenever there is an electron withdrawing group added to the carboxylic acid, that we see increasing the acidic behavior. Electron withdrawing group is nothing but minus I group. So it is going to stabilize the carboxylate ion, that is CO minus, and it will increase the acidic behavior. So let us see few examples here. So if we look at simply the acetic acid, we know acetic acid is a weak acid, that is vinegar that we use every day. Then suppose if one of the hydrogens is replaced with an electron withdrawing group like chlorine, then the acidic nature is going to be increased. Suppose if the other hydrogen is also removed, CH, Cl, Cl, COOH, then the acidic nature is even more increased. Then if the third hydrogen is also replaced with chlorine only, trichloroacetic acid is even more acidic. So as the electron withdrawing groups increase in the acid, the acidic nature also will increase. So minus I effect is directly proportional to the acidic behavior of the acid. Let us see the acidic nature in the cyclic compounds also with one more example. This is cyclopentanoic acid with nitro very close to the acid. Then there is acid and nitro is at ortho position. Then there is acid with nitro at third position. Now as the electron withdrawing group move away from the acid, the effect will diminish. So first compound is more acidic compared to second, and second is more acidic compared to third. So as the acidic nature acidic strength decreases, like the effect of NO2 goes down because of the distance, the acidic nature also will go down. Similarly, formic acid is more acidic than the other monocarboxylic acids. Like if you consider, formic acid takes the first position, then comes the acetic acid, then comes the propanoic acid, then comes the more substituted acids like. So what is the reason behind this? It's just the plus I effect. Methyl group that is added on to the acid is nothing but the plus I groups. Plus I groups will increase the electron density, so accordingly the acidic nature decreases. So plus I group is inversely proportional to the acidic behavior of carboxylic acids. Now these organic acids are generally less acidic compared to that of the inorganic acids. Now among the organic acids also we have aliphatic and aromatic. So compared to aliphatic, aromatic are more acidic. So aromatic acids are more acidic compared to that of the aliphatic acids. So if we look at but the exception is formic acid. Formic acid being aliphatic also it is more acidic. So formic acid being more acidic compared to benzoic acid compared to the normal alkyl or aliphatic acetic acid or aliphatic carboxylic acid. So this is the general information regarding the acidic nature of phenols and carboxylic acids with various examples. If you find this video helpful, please like, share and subscribe. Thank you.